Brain-computer interfaces analyze brain signals in real time to control external devices, communicate with others, facilitate rehabilitation, or restore cognitive functions. People think, and the computer does the rest. Research into BCI began in the 1960s when researchers implanted sensors under the skull via surgery. In the 1970s, the first non-invasive computer-brain interface project recorded brain signals from outside the skull. Up until the early 2000s, no more than 5 research groups were active in BCI software. Today, over 300 laboratories are focused on this area of research. Polina Anikieva is among the leading researchers in the field. Currently, she is an associate professor in materials science and engineering at MIT. Her research primarily focuses on the function and longevity of neural probes. In 2015, she gave a presentation at TEDx Cambridge where she presented on the future of minimally or non-invasive brain-computer probes. Currently, when medicine stops working on Parkinson's patients, doctors insert a millimeter-thick, 3-inch long wire into the skull to reduce tremors and other side effects. Although these devices yield mostly positive results, their side effects can be traumatizing. These methods often change patients' behavior entirely. So how come we are using such outdated technologies? Humans have successfully reduced the size of a computer from a multi-floored building to the size of a pocket. Why have such reductions not happened in the world of brain-computer interfacing? Polina is making breakthroughs in this type of technology. She has created a human hair-sized probe that interacts with the brain electronically, chemically, and mechanically. She uses fibers which are inserted alongside blood vessels inside the brain. The device tricks the brain into thinking that the device is a blood vessel so that it does not form a response. The image on slide 3 shows the material used and the fabrication process of this probe. Anikieva's team used microcontact printing and micromachining techniques to develop flexible substrates made out of polymers commonly used in medical devices. Images B, C, D, E, and F show close-up photographs and cross-sections of the probe. G, H, and I show the fiber's ability to transmit electromagnetic waves across different wavelengths and flexibilities. Although they were only tested on mice, the graphs show that her probes work at varying flexibilities, which is extremely promising. Anikieva's fiber devices can probe the brain to deliver similar therapy as the wires that exist currently. They can be used to quell Parkinson's tremors and have the potential to be used to treat depression or help amputee victims regain the ability to feel. Concurrently, Anikieva's team is looking into ways to hack the brain wirelessly and remotely. She is looking deep into the way that the brain functions. Her wireless technology controls voltages on neurons. Voltages are controlled by concentrations of ions inside and outside of neurons. Anikieva believes that if she can control the concentrations of ions, she can control the brain in its entirety. In her TED Talk, she asks the audience to imagine a neuron as a building. The neuron has walls and also doors. These doors allow ions to go in and out. One way to control the brain is to have the right key for the right door. The other way is to pull the fire alarm so that all the doors open. We know that heat controls many of the fire alarm mechanisms in neurons which open these channels. Because of this, Anikieva looked to magnetic radiation to wirelessly control the brain. Humans are transparent to magnetic fields. We can expose the brain to magnetic radiation covertly without people knowing. Anikieva's team of researchers inserted dissolved nanoparticles into the brain and applied a magnetic field to trigger brain responses. Only the groups of neurons that were surrounded by the particles will experience the heat and become activated, while everything else remains intact. The figure on slide 5 shows Anakiva's success. The first figure on the slide shows the process of exciting magnetic nanoparticles to trigger action potentials. As electromagnetic waves penetrate the brain, TRP1 channels excite and open, which triggers neural activity. Figures E and F demonstrate the differences in activity before and after electromagnetic radiation. In F, the dotted line corresponds to the crossing of the TRPV1 activation threshold temperature. As you can see, normalized fluorescent intensity changes as a function of time when the field is turned on. Remarkably, the waves triggered TRPV1 responses while avoiding non-specific thermal effects such as changes in membrane capacity. In the absence of MNPs, the magnetic field did not induce appreciable solution heating and no correlated response was observed. On the next graphic, B, C, E, F, G, and H show similar results. When MNPs are present and electromagnetic fields are applied, TRPV1 activates. Anakiva then tested her method on anesthetized mice, which shows promising results. Images A through O in the next figure show that TRPV1 opens in samples where mice were used. Using magnetic radiation, she has successfully triggered action potentials without wires, tethers, brain sockets, or tissue damage. Anakiva's minimally invasive technology remains on the frontier of brain-computer interfaces. However, other research groups have probed the brain in slightly more invasive ways that have yielded real results in real patients. Researchers at the University of Tübingen in Germany are researching ways that computer-brain interfaces can help paralyzed patients in the totally locked-in state communicate. In their study, they asked patients to answer basic yes or no, true-false questions while wearing a cap that monitors blood oxygen level and electrical activity in the brain. The computer calculates the differences in blood oxygen levels when the patients answer yes versus no and true versus false. After reading brain activity, their algorithm can decipher differences in patterns of blood flow during yes and no answers. The computer deciphers questions with known answers 70% of the time, which is outstanding. This research will alleviate the pain felt by families who can no longer interact with relatives in the completely locked-in state and will answer questions that patients have about care and comfort in hospitals. The image included on slide 6 shows the procedural flow diagram of the BCI for communication in ALS patients. The NIRS registers frontocentral oxygenation changes and the EEG tracks electrical changes in the brain. In the study, patients were given a 5-second rest period, asked a question for 1 to 2 seconds, and then given 15 seconds to respond. The image bottom left shows the position of source detectors on the brain. Although most computer-brain interface research is medically driven, computer-brain interface possibilities in media and communications, analytics, and marketing seem endless. Companies like Microsoft and Nintendo have recently incorporated human movement into games. But what would a game look like if we could get rid of controllers and control the game completely with our minds? A team at Opole University in Poland recently published a paper on the possibility of neurogaming. A challenge to neurogaming is the speed at which computers can process brain information. Video games are no fun if there's long lag between the controller and the gaming experience. The researchers realized that fast Fourier transform algorithms, a process used to convert a signal in the time domain into the frequency domain, can be used. However, a major hurdle remains in that brain calibration is extremely time-consuming, and neurogaming on the immediate horizon will require the use of additional controllers. Computer-brain interfaces will surely affect daily life in the near future. Like an avatar in the Matrix, futuristic humans will be able to directly engage their brain to carry out the daily processes that now require the use of cell phones or computers. Outside the medical realm, there are endless possibilities of brain-computer interaction. Internet connectivity will only augment such endeavors. What if you could communicate with others through thought? What if you could watch your favorite Netflix show just by thinking about it? Would this reduce the basic essence of humanity? Would computers slowly replace the need for original human thought? It is possible that brain-computer interfaces could go too far and endanger the definition of what it means to be human.